Today's webinar is part of a broader initiative known as the COSPACE webinar series, which brings together leading Horizon Europe projects to showcase how space-enabled innovations are shaping a greener and more resilient future. So COSPACE is a group formed of 5 Horizon Europe projects: Respondent, Magda, Swift, 100K Trees, and BuildSpace. And what these projects have in common is that they're all working on cutting-edge geospatial and AI-driven solutions to tackle climate change. It's supported by the Horizon Results Booster Programme, with COSPACE amplifying the impact of these respective projects by promoting knowledge sharing and collaboration. This is actually the first in a 2-part webinar series, with today focusing on the role of space technologies in energy and agriculture specifically, highlighting how Respondent and Magda are harnessing satellite-based forecasting, remote sensing, and AI to improve climate resilience. Our second webinar will take place on April 15th and will showcase the 100K Trees and BuildSpace projects, who focus on green cities and sustainable urban development. If you're interested in how space-based decision support tools are shaping future cities, be sure to register for that webinar as well. So why is this webinar important? Well, tackling climate change requires collaboration, innovation, and the smart use of technology. And I feel that's why today's discussion is so important, because both Respondent and Magda are at the forefront of integrating Galileo and Copernicus systems using AI-driven forecasting, remote sensing, and geospatial data to support energy security, sustainable agriculture, and climate adaptation. So in terms of what we can expect in today's webinar, we have an exciting lineup of speakers who will dive into topics such as how satellite-based forecasting enhances energy grid stability, the role of GNSS and Copernicus data in precision agriculture, and the broader impact of space-based enabled climate adaptation strategies. While we of course encourage everyone to participate and drop questions in the chat, there will be a dedicated Q&A session at the end of the webinar for people to openly discuss, ask questions, etc. Next up then, we have the demonstration of Respondent's power generation forecasting module from my colleague on the Respondent project, Andreas, who is also a front-end engineer at Future Intelligence Limited, which will then be followed by a presentation from Mirto, who is also on the Respondent project and is an R&D and AI engineer at Future Intelligence Limited. So yeah, the floor is yours, guys.
Hello, everyone. Thank you for joining us today. As Ben said, I am Andreas Tsarouchas. I work for Future Intelligence, and I am the front-end engineer of the Respondent solution. I'm so excited to introduce and walk you through the demonstration today, which will be focused, as Effie mentioned, on the power generation forecasting module of Respondent suite. I will walk you through the demonstration through the module's dashboard, which is a web-based user interface, showcasing the module's core functionalities and innovations. So before we start with the actual live demonstration, I would like to refer to the responsive design of the solution. And the primary use of this solution is designed for web application on desktops, as it provides a comprehensive dashboard experience that's best suited for large screens. And while the app is responsive and can display properly on tablets, it's not recommended for use on tablets or mobile phones due to the detailed nature of the interface, the amount of data displayed, and the complex interactions with the graphs and the charts. The dashboard's layout and functionality are optimized for desktop environments, allowing users to fully engage with the application's key features and analytics, offering a better user experience compared to using it on tablets or mobile phones. So as you can see here, this is the login screen for the Respondent solution, and the user, whether a renewable energy source owner, an aggregator, an administrator, will enter their credentials, and upon successful authorization, as you can see, if the credentials are correct, we will successfully and automatically redirect to the weather forecast module. So let's dive in. So, as part of the power generation forecasting module, we have the weather forecasting component, this one, you can see on your screen. And this component is responsible for monitoring both forecasted and real-time weather data for this specific photovoltaic plant. So the forecasted data here are generated using a combination of the following sources. The first one is the Copernicus Earth observation data. We also gather historical and real-time data from local weather stations and historical and real-time data from the photovoltaic plant itself. These data inputs are processed through our weather forecasting modules, which generate predictions for pressure, air temperature, air humidity, solar radiation, and cloud cover, which then are displayed in the following cards. So, starting with the first one, we can see the plant's detail card. And this card displays all the essential details of the plant, including its name, its status, online or offline, and its size with respect to the park's energy output. It also features an interactive map, as you can see right here. We can click on this icon right here, where again we can see the name and the status of the photovoltaic plant. There is also a home button that resets and focuses on the plant's location. Okay, there is the live data card right here. This card displays the latest real-time data from the local weather station in a table format. And as you can see the sensor type right here, the values of each sensor with the corresponding unit, and the timestamp that the latest data insertion was accomplished. So as you can see, it's live. Here are the latest values. And there are another 5 attribute cards for pressure, air temperature, solar radiation, cloud cover, and air humidity. So for the graphs, using the graph, you can see that each attribute card contains a graphical representation of both forecasted and real-time values. The x-axis displays the timestamps of the current day in 1-hour intervals, while the y-axis represents the attribute values. The forecasted series now are divided into 2 parts. As you can see, there's the past and the ahead. So past refers to the forecasted values from the start of the day and up to the current time, where the user is actually logged in and uses the solution. And the ahead series refers to the forecasted values from the current time and until the end of the day. And that applies to all the cards. So the graph has some functionalities. We can zoom in or zoom out to a specific time frame to see more details about our data. There is a home button that resets the graph to its original state. And there is a menu right here, as you can see, where the user can select and download the chart data into an SVG, a PNG, or a CSV format. Beside this menu right here, there is also an export chart data button right here, where the user can select again between an XLSX format or a CSV, and he can download the data for all the graphs. So as you can see, they're all live. We can hover to one timestamp and we can see all the values of all attributes in the rest of the charts. And this weather forecasted data is the key to determining the power generated. Moving on to the next one, this is the power generation forecast module. So this module consists of 3 cards. The first one, again, is the plants card, where we can see the name of the photovoltaic plant and its status, if it's online or offline. There is, it could be the case that there will be more than one photovoltaic plant. So this will be depicted here in a list format. So the power generation forecast card. This is the main feature of the page. And starting at the top right of the page, you can see right here, there is a switch button that allows you to toggle the unit of the graph. And the available options are the energy in kilowatt hours, and we can switch to power that is in kilowatts. Okay, so there is a control panel right here where you can choose to show hour intervals or quarter intervals right here. We can toggle with this switch the view to see 1 day or 3 more days, including this one. And there's also a button here for the exportation of the data, again in an Excel SX format or a CSV format. So this aggregation switch, as we said, as you can see, if I switch it, now the intervals are becoming into quarters. And if we switch back to hour, there's 1 hour intervals between the data in the graph. So this main card right here, again, you can see here the name of the plant, its status, and on the top right, you can see the coordinates of the specific photovoltaic plant. Next, there is a table presenting the performance statistics. So each row contains metrics related to the predicted values from the power generation forecast, along with the respective values and accuracy indicators. All of these metrics are described in detail by clicking this information button right here, located in the top right corner of the table. And upon doing so, a small modal will appear presenting all the relevant information and explanation regarding the metrics. This includes descriptions of each metric, as well as the associated accuracy thresholds. A more detailed description will be provided by my colleague Merton in the next presentation. So about the graph, as we said before, the x-axis here represent all the timestamps of the selected time frame, split it on 1 hour intervals or 15-minute intervals, depending on the selection of the aggregation period by the user. The default value is set to hourly intervals. And on the y-axis, as you can see, there are the values of the forecasted power with the corresponding unit. And as we said, by default, the initial state of this component uses energy as the pre-selected value for display. The aggregation period is set to hour, and there is the 3 days ahead forecast. So the series for the graph itself, it's the actual generation, which is the real-time data of the photovoltaic plant retrieved directly from the plant. There is the day ahead, so the forecasted power generation values for the current day and the next 2 days. The past estimation is like in the weather forecasting module. This refers to the forecasted values from the start of the day up to the current time, where the user is actually logged in and using the dashboard. And the upcoming production refers to the forecasted values from the current time and until the end of the day. As you can see, if we hover a point on the graph, and depending on the aggregation period, there is a tooltip displaying the values of all data series for the specific timestamp. Again, there is a control panel for the graph that we can zoom in or zoom out. We can reinstate to its original state the graph with this home button. And there is a hamburger menu again that we can download SVG, PNG, or a CSV format. So as you can see, this is for today. This is actually live forecasting data. And moving on, there is a small weather widget right here, which displays the temperature of the cloud cover as in the weather forecasting component. And starting from the current time and until the end of the day, this widget displays at hourly intervals the upcoming predicted values for either the air temperature or the cloud cover. We can switch to the temperature, we can switch to the cloud cover, depending on what we want to see right here from this button. This page refreshes automatically based on the selected aggregation period. So when the user has selected hourly aggregation, the page is refreshed every hour at the top of the hour. And if it's set to quarter, it refreshes every 15 minutes, specifically at 15, 30, 45, and 60 minutes of each hour. Last but not least, there is this timeline card right here. So this timeline card is an interactive feature that allows users to retrieve both forecasted and real time power generated historical data from the plant. Users can choose between three predefined time frames. This is set by default to today, which retrieves the historical data for the current day. There is the yesterday button, which retrieves the historical data and the predictions for the day before. There is the last week that retrieves historical data for the last 7 days, including the current day. And there is also a custom date picker, where the user can select a time frame ranging from 1 to a maximum of 7 days. And it's worth noting here that, let's say, if we go back 1 year, and we select a week to fetch the data. As you can see, the data are all here. And again, as you can see, all data are available. So this is an app for me. This is the power generation forecasting module. Thank you so much for attending this presentation. Ben, you have the lead.
Thank you very much, Andreas. That was great. And just to emphasize for everyone and for Andreas to confirm, that was live data you were using, correct? This wasn't taken from a few days ago.
Exactly.
Yes, so this is taken from a solar park in Greece, correct? This information?
Yes, yes.
Yeah, and it's happening right now. So just to emphasize the live nature of this demonstration. Great, thank you very much, Andreas. And then to finish off our presentations, as I mentioned, we have Mirtho Coletti from Future Intelligence Limited, who will present on the technical architecture of the module. Mirtho?
I am an AI R&D engineer at Future Intelligence, and I will show you some aspects of the power generation forecast module and some technical details of its architecture. So first of all, here we have an overview of the module. On the left-hand side, we have the different data sources. We have Earth observation data from the Copernicus program. We also have local weather station data, which are provided by Future Intelligence, by weather stations, and we also have actual PV power generated data. So these data are accessed via scheduled API call, via scheduled API calls, and used as inputs to our model. And the final forecast generated by this model is available via a user interface. So let's dive into more details about the models that we use. So this module is based on two models. We have a data-driven model, which provides predictions based on machine learning models. These models learn from patterns between historical weather data and actual PV power data. These models provide short-term forecasting and intraday, meaning from this hour up to the end of the day. We also utilize a numerical model, which uses weather forecasts from the previous model and also PV system characteristics, and it solves physics-based equations to provide a prediction, an extra prediction of the solar energy output. And this gives us a mid to long-term forecasting. And when we combine these models together, we can generate a final, highly accurate model that can leverage the strengths of the two separate models. So we will talk about its part separately. We can start from the data-driven solution, which, as I said before, is based on machine learning models. We combine two separate AI models here, and we can forecast from 1 up to 3 days ahead. And as I said before, we also have an intraday forecast, meaning we can provide a forecast of the remaining hours to the end of the day. And such a model, a data-driven model, is crucial for managing immediate operational decisions within the park. So after collecting our data, the data that I showed before, and we will see in more detail in the following slides, we feed them. This data undergo a feature engineering process. These new features are generated by this process, are used as input to our AI blending model, which produces this final optimized output, which is then showed via the user interface showed before. So let's see here an example of our data. On the top two panels, we have the temperature measured by our in-situ IoT-based weather stations, and the irradiance measured given by the Copernicus satellite-based weather data. And on the bottom panel, we have historical PV power data. These are examples of data, the actual data used in our models. So we have here some specifications of our in-situ weather data. So this table presents the main features of the sensors that are integrated in the weather integrated in these weather stations. The measurement data gathered from our sensors are transmitted to the FinApp Cloud platform through wireless technologies. You can see here. And what we can clearly see is that these data have high accuracy and high resolution, which is very, very important for such a task. Here we have an overview of the Copernicus datasets of the yes, and here we have some specific characteristics again. Here it's important to see that again these data have also high resolution, spatial and temporal, which is also very important for forecasting. So let's see now, after we collect our data, as mentioned before, this data undergo a feature engineering model. In simple words, we use this model, the principal component analysis model, which actually reduces the complexity of the data while retaining the most information. So in this way, we have our models can reach higher accuracy with lower computational cost, which is also very important. So now now that our features are ready, we can feed them into our models, our data-driven models. The first one is LSTM, long short-term memory model. This is a type of recurrent neural network. You can see its advantages. It's a model that can capture long-term patterns, which is important it's ideal for time series data like solar power weather data. it can be trained efficiently. It can also handle complex factors such as weather and irradiance, and it can adapt to changes as it can learn from evolving patterns over time. This model is, we use 1 year of hourly data, and we train our model to the 80% of this data, and we test on the remaining 20%. The second AI model that we use is LGBM, which stands for Light Gradient Boosting Machine. And this model also is very efficient at capturing complex patterns, and it can reach high accuracy with low computational cost. It can train fast with little memory usage, and it's also trained and tested on 1 year of hourly data as before. So now that we have trained our two models, we can blend them together into one optimal model, final model. In this way, we can leverage the advantages of the two separate models and increase the accuracy of our forecast. So here we can see an example of this combination. On the top panel, we have the two models, the two separate models. The red curve shows the LSTM model, the forecast provided by this model, and the LGBM forecast. The final hybrid model, the combination of these two models, is the green line, and we can see that the accuracy is higher compared to the two models separately. And on the bottom panels, we have the intraday prediction, which starts from the current hour and predicts the power generated by the PV plant up to the end of the day. And here we can also see that the accuracy is very high. So next, after we have our data-driven model, we can see the analytical model, the one that I showed in the very start. This model is based on established physical principles and equations that govern the behavior of the PV system. And this is a more accurate representation of the PV performance over longer time horizons. And it's very valuable if we want to have forecasts from mid to long term. So here we use forecasts of our weather data as shown on the top panels. And we also have specifications of the PV plant, such as the altitude, the coordinates, the tilt of the plant, etc. So if we combine these two, we can have a second prediction. So the final step is to combine the data-driven solution and the numerical one. We have an integration of these two forecasts, and now we can have a long-term forecast from 3 up to 6 days ahead. And in this way, we can capture both short-term fluctuations and longer-term trends in power generation. And in this way, we have very high accuracy compared to the two solutions separately. And here we have the final result, the final hybrid model. Here we plot the models separately, the LGPM and LSTM models, as shown before, the blue and red lines. Here we have a 3 days window, 3 days ahead window. The purple line is the numerical model, and the green line is the final hybrid model, that we can see that it has the higher accuracy compared to the other models. The numbers here are actually the error, meaning the difference between the model and the actual power generated by the PV plant. So a lower error means higher accuracy. So that's everything. Thank you for your attention.